Hello, welcome to Forest Learn. In this video you can have a go at a 1-mark question on gravitational fields, namely the energy required to launch a satellite into orbit. Let's take a look at it. Consider a mass m at rest on the surface of the Earth. The mass needs to be launched into a circular orbit a height h above the Earth's surface. See diagram. How much energy must be supplied to the mass in terms of m, little m, capital M subscript E, which is the mass of the Earth, h, capital R subscript E, which is the radius of the Earth, and big G, which is the universal constant of gravitation. Neglect air resistance. So you can see the diagram below here, referenced in the question. Please pause the video and have a go at this yourself. And when you're done, unpause the video and we'll discuss the solution. Okay, welcome back. To figure out how much energy must be supplied, we can break the problem up into 2 bits. The first bit is, how much energy needs to be supplied to raise the mass by a height h above the surface? To answer this, we need to consider the change in gravitational potential energy between these 2 positions or heights. Recall that in a radial gravitational field, due to a spherical planet, the gravitational potential, which is the gravitational potential energy of 1 kilogram, or a unit mass, is given by V, the gravitational potential, is equal to minus the gravitational constant, big G, multiplied by the mass of the planet, which here is just the mass of the Earth, divided by the distance r, which represents the distance from the center of the planet to the point that we're considering. So the gravitational potential energy of a mass little m that we're considering here at the surface of the Earth is the value of the potential at the surface, which is simply minus big G multiplied by the mass of the Earth, divided by the radius of the Earth, multiplied by the mass of the object. So recall, if this represents the gravitational potential, which is the potential energy of 1 kilogram, we need to multiply by the mass of the object, which is m kilograms, to get the gravitational potential energy of that object at the surface of the Earth. And similarly, the gravitational potential energy of the mass m when it's at height h, when it's raised by height h above the surface of the Earth, is going to be given by the following. The distance now is the radius of the Earth plus this extra height h above it. And what we're interested in here is the change or the difference in these gravitational potential energies. So the difference in gravitational potential energy, call it delta EP, is equal to this first term here minus this term here. And if we tidy up a little bit where these 2 minuses turn into a plus, we end up with the following expression. Now, supplying this amount of energy here is only enough for the mass to rise by a height h. Once it reaches this new height, it will be at rest and will fall back down to Earth. What we need to consider is the kinetic energy that the satellite would have in moving in this circular orbit. This is the second bit of the problem. Recall that if something is performing circular motion at speed v with radius r, the centripetal acceleration a is given by the square of the speed divided by the radius. And the radius here is just equal to the radius of the Earth plus h. So let's examine Newton's second law, which of course connects the resultant force on our object, or our mass m, and its acceleration a. We can replace a with the expression directly above. Now the resultant force here on the satellite is simply the centripetal force acting on it. And that's simply the gravitational attraction exerted by the Earth on the satellite. So we can replace F with Newton's formula for the attraction between two masses, which is given by big G, the gravitational constant, multiplied by the product of the masses, so the mass of our satellite, little m, the mass of the Earth, divided by their separation, the square of their separation. So we can equate that to mv squared over re plus h. It's useful at this point to cancel out a factor of re plus h on the bottom here and on the bottom here. So we've now got an expression for mv squared, which is equal to what's left over on the left here. And that's useful because from this we can easily get our expression for the kinetic energy, Ek, that the satellite would have in this orbit. Of course, that's just given by half mv squared. And that's just half times our expression for mv squared. So g little m big M, the mass of the Earth, divided by re, the radius of the Earth, plus h. So to find the energy that would have to be supplied, we simply add this kinetic energy to the change in the gravitational potential energy that we found earlier. And if you do that, and you tidy up and simplify it a little bit, you end up with this expression here in this rectangular box as our final answer for the total energy that would have to be supplied. If you found this question challenging, I suggest you try it again in the future as many times as you need to, until you can answer it comfortably by yourself. Students often complain that some 1 markers should be worth more than 1 mark, and I agree. This question is probably an example of this. However, I think tricky 1 markers are a very useful way to gauge where you're at. If you're having to think too long about a step, and can't proceed smoothly and quickly, it means there's room for improvement in your understanding. If you found this video useful, please like it, share it, subscribe to Forest Learn channel if you haven't already, and leave a comment. I'd love to hear from you about how you found this question. Was it easy or hard? And if so, what did you find challenging about it? Was the solution clear? And if not, which bits were unclear? Thank you for listening, and I hope to see you soon.